Okay, let's start. Usually when you come in, I'll have this screen displayed. This is just your login screen for WebAssign, and so it just shows the assignments plus the announcement. I haven't changed the announcements over here on the right-hand side, but on the assignments now, I have adjusted them slightly. So I added an assignment, but because we're going to start talking about using natural log to do integration, because it's really useful for that. In fact, that's why we created the natural log function, right, to help us integrate certain types of expressions. And so this is really an important homework, but we were still practicing with just differentiating the natural log last week, and we've still got a couple of examples to do from the notes for that. So originally this homework was due today, but I shifted it back to Monday so we can finish all of our examples. And I also wanted to look at a couple of problems in that homework just to show you some things that I've added to the homework that will be on this assignment and other assignments as well, so to look for them. They're things that can help you sometimes with the homework assignments. So we'll look at that well in just a second here. But then I added again, I added that homework assignment, but that's not due until looks like 2 weeks from today. And then don't forget the calculus review, right, which is due at the time of the first test. Okay, so just slight updates there on the assignment. So I didn't look and see how many people have worked on this assignment or how much progress has been made on this assignment. So I'm not sure what that is, but keep working on that. So we'll probably keep this due date, right, Monday at midnight. So we'll still have a chance to ask questions about this assignment, either in class on Monday or at Taylor's SI session on Monday. Okay. And then the Academic Support Center is open. So North 925, the walk-in tutoring center, is open, so you can walk in anytime. And so that's open, and people there can also answer questions about Calculus 2. Although you may occasionally go, and there may not be so Calculus 2 is getting a little bit more specialized. So you may go, and sometimes they may say, well, we don't really have anybody now that can answer questions about Calculus 2. So you might have to investigate a little bit about when there are tutors available that can answer questions about Calculus 2, or in particular tutors that you like are available that you can ask questions about Calculus 2. But a lot of people last semester used the Academic Support Center. A lot of people in my fall class used Academic Support Center a lot, and they did well. So I think that's a good place to go, okay, to get help. All right. So that's all I want to say about the homework right now. So do y'all have any questions, your own questions that you want to ask me currently? Anybody? About anything? Do we have anybody new today so that Taylor can give you a syllabus? Nobody new? You're new? Okay. All right, so Taylor will give you a syllabus. So you're going to have to read that syllabus, and in particular, it will have instructions on how to get enrolled in WebAssign. And the free access period is still ongoing, right? So that will continue until Monday. So you'll still have opportunity to, without purchasing access, right, you'll still have opportunity to continue working on it. So you can enroll today if you just follow the instructions in the syllabus so that you can start working on that homework assignment, okay? So if you're not going to purchase access immediately, you may want to try to get this one done, right, okay, so that you don't want to run out of time, right, before that one is due, okay? If there's a lapse between the free access and when you actually purchase access, none of your work will be lost. Okay, so when you purchase access and you resume working, then all of your previous work will still be there. Yeah, were you trying to ask a question? I keep talking over you. Or were you just looking through your notes?
No, I was asking a question.
Oh, okay.
Like, if we have a question about last class?
What now?
About last class?
Oh, sure. Yeah.
Can you go back and talk about how, like, the last question, but on the second to last example?
The second to last example. Let me see. So is it this one?
Yes.
That one? Oh, okay. All right. So, do you have a specific question or just what happened?
I tried to redo it, but I didn't get.
The same thing? Did I make a
Yeah.
mistake? Let's
No,
see.
I don't think you made a mistake. I think I made a mistake, but I don't know where I
All right, so well, we're gonna practice this again pretty quickly. All right, so this is a good opportunity to review because we're gonna do this problem. You're gonna do this problem. We're gonna do this problem together as a class, right? Okay, and that's really as hard as they get in terms of differentiating the natural log function. All right, but well, we haven't seen this for a week, right? So let's remind ourselves there. So here we have natural log of square root of x plus 1, and we want to find the derivative of that function, all right? Or you can think of that as an expression, okay? So one thing you can do that frequently is helpful, right, when you're working with natural log functions is to apply properties of the natural log function, right, in order to maybe expand that natural log function into simpler natural log functions. And that's what we're going to do right here. So in the typical calculus fashion, right, since we have a square root in this expression that we're trying to differentiate, right, we're going to first, so this has nothing to do with natural logs, right? This is just a standard calculus practice. We're going to convert that square root to a fractional exponent, right? Okay, so we frequently do that in calculus, right? Especially when we're differentiating. So I'm going to or integrating actually. So I'm going to take that square root and write that as an exponent. And remember, square root corresponds to 1/2 power. You really have to remember that. Okay, all right. It's really good that you remember in general how to convert radicals to fractional exponents, but the one that occurs most frequently is square root. So you've got to really remember that square root means 1/2 power. Cube root means 1/3 power, right? Okay. So we're going to write this as x plus 1 to the 1/2 power, rather than square root of x plus 1. Now, the reason that's really an advantage here is because remember when you so we can apply now a property of natural logs. So when you have natural log of a power, right, okay, a quantity raised to a power, then you can simplify that by taking the power and writing it as a coefficient. So what that does is it converts an exponent problem to a multiplication problem. And usually it's easier to multiply than it is to raise a number to a power. So that's the advantage to this, okay? So we're going to simplify the expression a little bit by making that square root, right, which is, it's hard to compute square root sometimes, correct? Right? And we're going to convert that into a product. So just 1/2 times the natural log of x plus 1. But it's easy to multiply numbers by 1/2. You can do that in your head, right? Okay? So that's why that is helpful. All right. Now I'm going to actually take the derivative. So none of this was differentiating yet, okay? That was all just rewriting the expression, right? Now I'm going to take the derivative, okay? So when we take the derivative here, we have a product, but this factor is just a number, right? So we don't have to worry about using the product rule here to take the derivative, right? We can just keep the 1/2 and then take the derivative of natural log of x plus 1, okay? So that's what I did. I kept the 1/2 and then I took the derivative of natural log of x plus 1. But as we learned last week, right, the derivative of natural log, what does that do? That just gives you the reciprocal, right? So natural log is easy to differentiate, right? Okay, if you have natural log of an expression, it's just going to be the reciprocal of the expression. So the derivative of natural log of x plus 1 is going to be 1 over x plus 1. But the one catch, always a catch, right? The one catch here is since this expression is not just x, but it's a little bit more complicated than just x, right? You have to keep in mind the chain rule. So you must also then at the end, this is the chain rule, multiply in the derivative of x plus 1. But fortunately, the derivative of x plus 1 is 1. It's easy, right? Okay? So that doesn't really make, the chain rule here doesn't make much difference in this problem. So you just get 1/2 times 1 over x plus 1, and that's 1 over 2 times x plus 1, okay? You can write that as 1 over 2x plus 2 if you like, okay? But you can leave it in this factored form as well, okay? Does that make sense? Did you see where you made a mistake?
I for the 1/2, I changed that into like a non, like I just took it off. Like I just put 1/2 and I thought I would get the derivative and I thought it would just be like nothing.
Oh, the derivative of 1/2 is 0? Yeah, the derivative of 1/2 is indeed 0, okay? But that's not the way you're going to differentiate this product, okay? You'll keep the 1/2 and then take the derivative of The x plus 1. Yeah, the natural log of x plus 1. That's really the product rule, okay? But it's a shortened version of the product rule because this is a constant. See, the product rule actually says to differentiate a product, right, you have to take the derivative of this times this plus this times the derivative of this, right? So you were sort of thinking that. First, I take the derivative of 1/2 times natural log of x plus 1. But what's the derivative of 1/2, you said? 0. So you would have 0 times natural log of x plus 1. But that's 0, right? But that's only 1/2 of the product rule. The second half of the product rule says keep the 1/2 and multiply by the derivative of natural log of x plus 1. That's where we ended up with this, okay? But in the first half of the product rule, you took the derivative of 1/2, which was 0, times this. So the first half of the product rule is missing, right? That's gone here. But the second half is still there, okay? Right, yeah. All right. All right, well, okay. So we're going to come back and look at this example. Before I do that, though, let's look indeed at the homework, because I want to show you a couple of things that are useful in the homework. So let me open that. All right. So there's the homework, and notice at the top, okay, there are some things filled into this instruction. Right, and sometimes there are things filled into the description. You may have to open this though, because I think you can open and shut these. See, you can shut the instruction, so you may not see that. So to see that, you want to open it, right? Same thing for description, okay? So if there's something there, you want to open that up. All right, now, here's what's there, though, okay? I have a link here to a screen that you can use to help you with just some things that, some operations, some tasks that might be useful in the course. And one of them is sometimes we have to graph functions, right, okay? So sometimes it's useful to graph functions. So here's a screen that can help you graph functions. This is a Desmos screen. That was the software I was using last week. We're going to use it again today, okay? And we can do lots of things with Desmos, but the most basic thing you can do with Desmos is make graphs of functions, okay? And in this homework, you do have that opportunity to do that, okay? And so if you're not using a graphing calculator, you can just do this immediately in your homework. So see, on problem number 1, very first thing it says is sketch the graph, okay, of 7 times the natural log of x. Okay, so this is not even really a calculus question. They just want to have you graph this and look at the graph and see if you can tell what the domain is, right? Okay, so well, of course, since it's an online homework problem, they're going to show you some graphs and then ask you to pick out which one is the correct graph, right? Okay, so if you're wondering about that, then you can go to this screen, right? Okay, and this screen just does, all this does really is just basic graphing for you. So all you have to do is change this formula, and then it will draw the graph for you, okay, over here on the right-hand side. Now, what you may have to do sometimes, however, is adjust the graphing window, because the portion of the x and the y-axis you're looking at, of course, is going to alter the appearance of the graph, right? So sometimes you have to adjust the graphing window. I'll show you how to do that also, okay, in this software. But let's see, if we just make this graph, let's see how it comes out, because maybe we don't really have to mess with the graphing window that much for this simple function. So let's see, what was it? 7 times natural log of x, right? So Desmos knows natural log, so if you just type in ln, okay, it knows that, right? So I just typed in 7 ln x, right? And there's the graph, okay? And so so we can compare that, right, to the ones that they gave us. One way you can change your graphing window, by the way, in Desmos is dragging this screen around, right? So if you point at it with whatever you're using for your mouse device, right, and then hold that down and drag it around, right, you can change the graphing window that way, okay? And there are other ways of changing the graphic window as well, right? You can magnify it or reduce the magnification through the plus or the minus button. But if you want to do really careful resetting of the graphing window, I'll show you how to do that in just a second. You do that in this list of settings that you get to by clicking on that little wrench icon. Okay. All right. Well, let's see. So if we blow this down, right, it looks like this. Or if we zoom in, we can make it bigger if we want to, right? Which one is the right one there? Okay. So let's look at this carefully before I switch back there. Let's see. So it's increasing, right? It looks like it has an x-intercept right here that looks like 1, correct? Okay. And then at 2, it looks like it's up pretty close to 5, right? Okay. So can we see the one that's the right one there? Which one looks right there? It's not this one. Wrong x-intercept, right? Not that one. Not that one. So I guess the only possibility is the first one, correct? Okay, so A had to be the right answer. That looks pretty close, right, to what we were looking at. So the right answer there is A. Oh, by the way, now what's the domain? Can you tell that from the graph? So what would the domain be? Where does the domain start at? 0, right, but not including 0, okay? So a natural log function does not include 0 in the domain, and then it's going to extend all the way to positive infinity. So this graph is actually going to continue increasing like this, and it extends all the way to the right along the x-axis. So the domain is 0 to infinity, not including 0, okay? And of course, not including infinity either, because well, you can't include infinity, right? Because that's not a number. Did y'all see? Let's see, how do I do that now? So if I want to type that in, I think the parentheses you can just type, okay, off of the keyboard. Whoops, but I didn't do that right? Okay, so parenthesis, and then 0, comma, and then we want that darn infinity, right? So did y'all see where to find the infinity there? You use the math palette here on the that pops up, right? So is it under symbols?
Yeah.
Okay, so look under symbols there, and there's infinity, right? Okay, so there's the correct domain for that function. Okay, so see, all right. So what could have been a hard homework problem is really a pretty easy homework problem, right? When you're using, when you're just doing the graphing with the computer and using WebAssign to type in these expressions, right? Okay. Now, it gets a little bit harder, okay, as you go further down the homework. So let's scroll all the way down to the bottom, okay? Let's scroll all the way down to the bottom. So this is the last problem, so it should be the hardest problem, right? Okay, and it kind of is the hardest problem. Yeah.
I have a question though on
Number 3. Hang on a second there. So, oh yeah, yeah, I should have mentioned this one too. I had all sorts of. I have already had several questions about this one. So if because it asks you for 4 decimal places, is that correct? Yeah. So that's a lot of decimal places. So what's going to happen is when you do this you're going to do this with a calculator, right? Okay, and I think all of these require a calculator, right? Yeah. Okay, so you're going to do this with a calculator, and then your calculator result and the WebAssign result are going to maybe slightly differ, like in the last digit, okay, of the 4 decimal places. So if you think, I know I've got this right, but you can't get WebAssign to agree with you, email it to me through Ask Your Instructor, right? Is that on here? I think you have to answer first or something like that, right? Email me, and then, or is it up here? Oh, yeah, here it is. Ask your teacher, and I will tell you what the right answer is. Don't burn up all of your choices, okay? Have you already done that? Because that I can't fix, all right? So, yeah, so, but that's, if you're doing the problem right, okay, that's really a key thing there. The few points there are not going to, in the long run, make any difference to your overall grade. Yeah, I know it's frustrating, though. Yeah.
For ABC, you're just going to type out exactly the 4 digits that you get, but for D, you're going gonna round that one to the last 4 decimal places.
Oh, I see. So, so you think there really is a reason for WebAssign giving the answers that they give, or yeah?
That's what how I ended up getting them correct.
Oh, I see. No.
Because when you go to the practice,
I had students come to my session today, and it's just a round off error. Like they're just not. It's not rounded correctly.
when you go to
Okay. So you're saying WebAssign is just wrong?
I think we're WebAssign.
Yeah, it's possible WebAssign.
They had a float of like 10 decimal places,
Oh.
and it was just not rounded correctly.
Oh, okay. All right. Yeah. So that's possible too. That
But
WebAssign is.
some people get it right. So
Yeah.
it wasn't.
Well, because these are randomly generated problems, so some people get different values. Okay. So so if if you think, yeah, I know this is correct, email me, right? Okay, and I will tell you what the right answer is. All right, what to enter there. Okay. Everyone who's emailed me has been right, except in the last decimal place by 1. I tried to adjust the setting. I can adjust settings in WebAssign when it grades you, so it has some tolerance, but though I'm not, those settings are not always do not always function properly. So sometimes it is really strict, and I can't get it to stop. Okay, so all right. Thanks for that question, though, because I've had that. All right, let's look at 16. Okay, because this is the hardest problem, I think, in some sense, right? So it's kind of hard to actually even read. All right, so it says the term in years, so that's how long you're going to be paying, okay, for a $200,000 home loan, all right, at this interest rate, okay, 7.5%. That's given by or approximated by this function where X is the monthly payment, right? So, of course, how long you're going to be paying on the loan, right, this amount of loan at this interest rate, of course, is a function of what your monthly payments are, right? If you lower the monthly payments, you'll be paying longer. Or if you increase the monthly payments, you'll have to pay for a shorter amount of time, correct? So here's the formula that actually will tell you at this interest rate for this amount, right, how long you have to pay, right, based on what a monthly payment is that you're going to make, right? And so first question there is very straightforward. It's just asking you to graph this, right? So you can use Desmos, right, to construct a graph of this function, correct? Okay, but of course you'll have to type in the expression in Desmos, right? So that does take a little bit of work, and you also will have to adjust the graphing window, right, so that you can see the graph. If you just type in this expression in the default window for Desmos, you won't see anything. It doesn't mean that the curve's not been graphed. It's just that you haven't picked the correct portions of the horizontal and vertical axes, right? The way you do that in Desmos, change that horizontal and vertical graphing window is, as I mentioned earlier, right, is go to the graph settings here, the wrench, and click on that, and notice it will allow you to reset the upper and lower bound for the x-axis, right? So you can reset that to whatever values you want, okay? And you can do the same thing for the y-axis, right? So just type in to these blanks, right? The starting x value, the ending x value you want, the starting y value, and the ending y value you want, right? Okay. So take a look at your choices there in problem number 16, okay? And you can reset the graphing window, right? And then find the correct graph there, all right? So graphing for that problem, and then the next thing though is because there are several parts to this problem. If you go all the way to part D, right, okay, it's going to ask you this, all right? So it says find the instantaneous rates of change of t, right, with respect to x. So remember, t was the output variable from that function. That's the term, the length of the that you're going to be making your payments, right? X was the input variable. That was the size of the payment, right? So they want to find the instantaneous rate of change here of t when x is 1390, and then a second value for x when x is 1610, okay? Now, here's what you have to remind yourself from Calculus 1 to do this problem. What does instantaneous rate of change mean? So what is the instantaneous rate of change? What's another more common term for instantaneous rate of change? Slope of tangent line, but what's a more common term for slope of tangent line? Derivative, right. It's derivative. Okay, yeah, all right. So what they're really asking you here in more familiar calculus language is what is the derivative, okay, right, when x is 1390 and then also when x is 1610. So they sort of indicate that in the notation, right, okay? They want you to evaluate the derivative at 1390 and then they want you to evaluate the derivative at 1610. So that means you have to compute the derivative, right? If you're going to do this by hand, you'll have to compute the derivative of that original function, correct? And then plug in for x 1390 and plug in for x 1610, okay? Now, I think you can calculate that derivative, right? I think you can compute that derivative, or you have the tools to compute that derivative, right? Okay? Because this derivative merely involves what? What's that? Natural log, right, okay. That merely involves a natural log, and you know how to compute derivatives of natural logs, right, from this section. So I think you can calculate the derivative of this expression and then just plug in the 1390 and plug in the 1610. You may have different values in your homework, okay. All right, however, I'm going to give you a little shortcut here, all right, to doing this, all right. I have a second Desmos screen here, okay, that is available, all right? So this is why it's useful to read the instructions, okay, at the top of, when I give instructions with the homework, or sometimes the description for a homework, okay? Notice it says, look, on the second instruction, it says, use the following Desmos screen to help you compute and evaluate the derivative in problem 16. Okay, all right. So if you don't want to calculate that derivative by hand and evaluate it by hand, we can have Desmos do that for us. All right, and here's what you do: just click on that screen. Okay, and it's pretty easy. All right. All you have to do is type in your function formula. Okay, so that's the formula t equals whatever that is, right? Okay, with the natural log, correct? And then just put in a value here, and it will evaluate the first derivative for you at that input, okay? So you wanted to type in for this, what was it, 1390 and 1610, okay? But first, of course, you have to enter in that formula with the natural log. But you don't have to calculate the derivative. Desmos will do that for you. All right. Let's see. Is this correct, by the way? This is not our problem, right? But this is just a sample problem. Let's see. If our function is x squared minus 5x, and we want to evaluate the derivative at 0, does that turn out to be minus 5? Okay. What is the derivative of x squared minus 5x? 2x minus 5. And if you plug 0 into 2x minus 5, what do you get? Negative 5, right? So at least here, okay, this is correct, right? Okay, so so you can maybe save yourself a little bit of work with your calculator in problem 16 by using this screen. Okay, that was just meant to be a time-saving device for you there, right? But you do have to type in the formula for the function. That's kind of its own special issue, right? Okay, typing in that formula in Desmos. Okay, by the way, you can use the slash in Desmos on the keyboard. You can use the slash to create a fraction. If you're wondering how do I build a fraction in Desmos, just use the slash for the keyboard and it will create a fraction for you. All right, so those are the things I wanted to mention from the homework. But if you have other questions on Monday, right, okay, other questions on Monday, then be sure to bring those so that we can settle those before the homework is due on Monday night. Okay, did you pass the rollout yet? Okay, so Taylor's going to pass the, I think everybody's here now. Taylor's going to pass the rollout, so we're going to do the same thing as last time, right? So if you're new, you're the one new person. You will sign in slot 28, okay, because that's the first available slot. We filled up 27 last time. Remember to sign in the same slot you signed in last time, right? Now, I have conveniently here, if you forgot your slot, okay, I have conveniently attached last time's sheet, right, so you can look at where you signed, right, and make sure you sign in the same slot. Do not use someone else's slot. This always causes issues, okay. every semester, people signing over other people's slot, and there's all sorts of nasty repercussions from that. Okay, so don't do that. Okay, but do make sure you sign, right? Remember, there is an attendance policy. Okay, whew, finally. All right. I'm tired of talking now, so I'm going to give y'all a chance to do a little work as promised, right? Okay. So, wow, this is a terrible one to start with here. Let's try differentiating this expression. So we're just trying to find the derivative, right? So if you can differentiate this expression, then you're in really good shape, okay? Because that's about as difficult as they get with differentiating natural log expressions. There's nothing in the homework that's going to be any harder than that, right? So we want to find what is the derivative of the natural log of x times x squared plus 1 squared over the square root of 2x squared minus 1. Remember now, before you haul off and try to compute the derivative, what do you want to do first? Expand it, right, using all those natural log properties, right? Okay, so you want to break that up into multiple natural logs, right? It could be sum of natural logs or difference of natural logs, right? Okay, break that down as best you can, okay, using your natural log properties. Once you've done that, then you can go back and compute the derivative, right? That will make it much easier, okay? Do not forget, when you're computing the derivative, do not forget the chain rule, though, okay? Do not forget the chain rule. That's going to come into play twice, I think, in this problem, okay? All right, at least twice. All right, but I don't think you have to use. You don't have to use the product rule, and you don't have to use the quotient rule. Those are not necessary in this problem because of the natural log properties, okay? So you don't need those. All right. If you break that down properly. Okay, so everyone try this, and Taylor and I will watch you and see if you seem to be getting the steps right. Okay, so try to get as far as you can to it before I call time there, right? Okay, and you can also answer questions of Taylor and me, right? So how do you get started there, right? So you want to use the log properties. So here you have log of a quotient. How can you break that up? Remember, if you have log of a fraction, how can you break that up into different logs? Log of a fraction is what? Were you here last time? Oh, today is your first class? Okay, so why didn't you say that just a moment ago? All right, so. Yeah, I know, but I just asked who was here for the first time. Did you not? Okay, all right. So you will sign in, when you get the roll, you will sign in 29. Okay, you will sign in spot, so that will be your slot to sign in every time. Okay, all right, 29. All right, so and Taylor will give you or I will give you a syllabus. Okay, because you've got to get on the WebAssign homework. Okay, but the instructions for that are in the syllabus. Yes. Do you know how to break these things down yet? Or you? Okay, all right. Mm-hmm. Right, but this is your first time attending, right? Okay, all right. So hang on there, and we'll show you. We'll eventually show how to do this. Okay, all right. But let me tell you that the lectures from last week, the 2 lectures from last week, are posted because I taped these, and so they're in the Blackboard page for this class. If you go to the link that says class notes and videos, you can actually watch the videos for last week. Okay, yeah. All right, so y'all will just have to hang on for a second, and then watch me when I do this. All right, so are y'all breaking this down?
This is how far I got it.
Okay, so all right, so this you can break up though first, right? Because that's log of a product. So what's log of a product? How can you break that up? There you go. Right. Yeah. Yeah.
And then minus
No, but the 2 is still there.
What?
This 2. Yeah. Right.
Yeah,
No. Put it here. No. Not yet. You can't put it down there yet. Yeah. So now it's there, right? Okay. And then minus, and now 1/2 ln of.
2x2 plus 1.
Yeah. There you go. Now you can bring the 2 down. Okay. There you go. Now that's broken up. Now compute the derivative, right? Okay, now you can compute the derivative. Got that? Okay, right. So how are y'all breaking that up right there? So you get this, looks perfect, looks nice. I like that, okay? So what'd y'all write down here? This, perfect. That is right, yeah, because that's the chain rule, correct? And then minus the 1/2 this, and then, lovely. Yeah, right. Because 2, this 2 will divide into this 4, right? So you will end up with 2x there. Yeah. Well, fast. Great. Love that. Okay. Wow. So they can show you. They can show you what they did. Yeah. Okay. But you're on the right track, I think. Right. Okay. So, all right. Let's see. Where did you start?
I started and I'm like, no, this is not right.
All right.
Okay,
So first, let's think of applying our log properties, right? So you have log of a fraction. So how does that break up?
So log of x and then log of this.
Not quite. You're going to get there. But first, what we're looking at is we have this fraction,
Yes.
right? So how do you break up log of a fraction? Log of a over b is what?
Log of a
Mm-hmm.
plus log of b.
No, fraction is
minus.
minus, right? So you would have log of the top
Yes.
minus log of the bottom. That's the first step.
Yes.
Now you have a product, right?
Yes.
So now you can break this up as log of as a sum of the logs. And then another thing you can do here is remember square root. You can convert that to 1/2, right? Yeah, right. Right. Okay. So that's and then all right. So that's how you get started there. Did y'all do it? Right. I think that looks good there. Yes, I think that is correct. Very good. Okay. Now, while y'all are
I'm
very
gonna right now.
all right, so he will explain it to you because he's got it. I think not quite because you have forgotten the all-important chain rule, right? Remember, when you take the derivative here, right, you do have to take the reciprocal. You did this. But then you have to multiply by the derivative of x squared plus 1, which is what? Now, yeah, and then there's a minus sign there, I think, right? And same thing there, you have to multiply by, there you go, right. Now you can simplify that a little bit, but that's essentially correct. Yeah, okay. Okay, so let's see how you broke it up. So you got natural law, you got this, so this is all nice. Now, yeah, so write d over dx there just to show that we're taking the derivative, right? Okay. Now, all right. So now we have to remember how do we differentiate natural log? Do you remember what's the key step there in differentiating a natural log?
I just know this comes out to like 1x. Like
That's it. Yeah, that is the key step. Derivative of a natural log is going to give you reciprocal. Okay. All right. So how would we differentiate this? The 2 is going to stay, so because that's just a constant. But how would you differentiate that now?
Yeah, that's why I was getting confused at.
Yeah, but you do the same thing you did here, right? You have natural, yeah, you take the reciprocal. Okay. So keep the 2 times, right? And now,
this?
Yeah, this. What's the reciprocal of that? Reciprocal.
Like that?
No, reciprocal.
Oh, oops.
See, here you had natural log of x. You wrote 1 over x. So here you have natural log of this, so you're going to write
like,
what?
It should be like that, right? And then you put that here?
Yeah, it should be, you're just right at it there. It should be 1 over this, right?
Oh.
Reciprocal, right? So keep the 2. The 2 is not in the denominator, by the way. The 2 is just multiplied out here, right? But it's 2 times, and then take the reciprocal, right? Always take the reciprocal. But the catch here is this is not just x. This is x squared plus 1. So you have to multiply in its derivative also. That's the chain rule. What's the derivative of x squared plus 1?
2x.
2x. So also multiply in here 2x. Okay? Did you hear that? Is it Chris? Did you hear that? All right, now, all right, so, yeah,
Like that, and then you have to find the derivative.
Yeah, which is 2x. Now, what about this one? Sort of the same, right?
Sort of the same, this.
Uh-huh.
And you take the reciprocal of this, right?
Right.
That's gonna be 2x 2 minus 1.
And then times what?
The derivative, so it's like
Yeah, what's the derivative of that?
4x.
There you go. Yeah, right. Now,
And then
that's it.
if you go
Don't forget you have a plus here and a minus here, right? Yeah.
right here.
Yeah, there you go. Now you can simplify that a little bit because this 2 times this 2 times this 2x would be 4x. This 2 will divide into this 4x. So you can simplify that a little, but that's essentially it. That's the answer, right? That's
The
it.
whole thing?
That's
Like,
it.
I thought we had to do like power rule something, like where it's like,
Mm-mm.
it is power rule because derivative right here.
No,
Something like
that's
that.
it. Nope. Mm-mm.
Mm.
That's it. You're done.
Oh,
Okay? Right. All right. So did you get it broken up there? That 2,
It goes over here.
it will actually go over here because first thing that's going to happen is you will have, let's write it. First thing you'll have is natural log of x plus natural log of this squared. Okay?
Okay.
Yeah. And then now you will bring this 2 down, but it goes here. It doesn't go here. So you get natural log of x plus 2 natural log x squared plus 1 minus 1/2 natural log of 2x squared minus 1. Right. Now that's just breaking things up.
Yeah.
Now differentiate. Now you differentiate. Okay? All right. Now you differentiate. Did you finish that one?
I'm working on it.
Yeah, this is x squared plus 1, right?
Oh,
Yeah. But I think this is already correct, right? I don't think you need to.
that should be all.
Yeah, that's it, right? You don't need to do anything else. That's it.
Alright.
Yeah. Okay. Don't try to add those or subtract those fractions. Just leave them in this form. What did you get there? Is
I was
there
confused if
a?
I
No,
hit-
that's right.
Is
I
that right?
think.
You can cancel that one out.
Let's see. But yeah, but isn't that a 4x there?
Yep.
Because
Yep.
yeah. All right. Did you get it there? I think that's right. Nice. Except there's a minus sign here.
Oh, right.
Right, because, did you get it?
I'm not sure. I think
Okay, so, yes, let's see, no, you're missing a 2 here. You
Okay,
dropped your x,
yeah.
oh, you did your exponent too
yeah.
soon.
Yeah.
Yeah, okay. You actually have to first break this up and
Okay.
keep the exponent here, and then just bring the 2 down here. It doesn't go
Okay.
in front there, okay? But your idea is essentially right there, okay? All right, did y'all get it?
This is how far we got, because this is where it threw us off. We don't know if the 2x is going to be in the front or is it going to be in front of the natural log.
Okay, so you didn't. So you have natural log of x times x squared plus 1 squared, right? That's a product. So you can break that up. You can break it as natural log of x plus natural log of this. So scratch out that 2. That 2 shouldn't be there yet. Okay. Now you can break that up as a sum. Yeah, natural log of x plus natural log of x squared plus 1 squared. Yeah, natural log of x squared plus 1 squared. X squared plus 1, all of that squared, right? Minus, and then the 1/2. Yeah, because remember it was squared to start with, right? But now you can bring the 2 down here. Yeah, do it later, right? Okay. Now that's just rewriting the expression. Now you have to differentiate though, okay? Right? Because we haven't differentiated yet, right? Now you differentiate each one as you go.
For this one,
This 2 you
because
can
of the
bring down,
product.
right? Yeah, you added it because of you can change natural logs of products to sums. Yeah, right.
So this is what it counted as first. So it wouldn't be just one whole since it's just the numerator, or you can also break down the numerator with the rules.
What we did was do 2 things there. First, we broke up the fraction as difference. Then we broke up the top as product.
Okay.
Yeah, but now this 2 you can bring down.
Oh, okay.
Yeah.
So then it
Now you can bring this. It wouldn't go here. It would go here. Because this is not squared, but this is squared, right? So the 2 will go down here. Yeah. Okay. Yeah. 2 times ln. 2 times ln of x squared plus 1. Now you differentiate. Okay. Now you have to differentiate. All right. Okay. All right. Let's look at that. Y'all did really well, so that's good. That was better than I had hoped there, okay? On this tough problem after just a week, okay? All right, so first thing we're going to do is not worry yet about taking the derivative. We're just going to, as I mentioned, expand this natural log, right? Okay? Then we'll worry about the derivative. So this is first, notice this is natural log of a quotient, right? Natural log of a fraction. So when you have natural log of a fraction, remember, you can break that up as natural log of the top minus natural log of the bottom. All right, so that's the first step, right? Top minus bottom. Okay. All right, now, but we're going to keep going here, right? Now we have natural log of a product. Okay. So remember, you can break natural log of a product up as sum of natural logs. So this would be natural log of x plus the natural log of x squared plus 1 squared minus, and while I'm at it here, let's rewrite that square root as a 1/2 power, right? Okay, that's I didn't write that very good. That's supposed to be a 1/2 exponent up here, right? Okay. Now you've broken up your quotients and products, but we have these powers, and remember, when you have natural log of a power, you can bring the exponent in front as a coefficient, right? So I can still rewrite this as natural log of x plus 2 times the natural log of x squared plus 1 minus 1/2 times the natural log of 2x squared minus 1. All of that now that's not calculus, all right? All of that is just applying the natural log properties to simplify that natural log expression. Now we're going to compute the derivative, all right? But it's going to be much easier now to compute the derivative of this expression than the original one. All right, so I have derivative of, I have to rewrite all of this. Natural log of x plus 2, natural log of x squared plus 1 minus 1/2 natural log of 2x squared minus 1. Okay, all right, so how do we differentiate this now? Just term by term, just go term by term and take the derivative. This is the standard derivative, right? What's the derivative of natural log of x? 1 over x, right? Yeah, that's the basic rule you have to remember. Derivative of natural log is 1 over x. You take the reciprocal. Now here you have this constant 2 times a natural log of x squared plus 1. So you can just keep the constant in your derivative and then take the derivative of natural log of x squared plus 1. That, again, it means you have to take the reciprocal. So you write 1 over x squared plus 1. But the complication here, as it is almost always the case, is this is not just natural log of x. This is natural log of an expression involving x, a more complicated expression involving x. So the chain rule comes into play here. You have to multiply in the derivative of x squared plus 1. But that's easy. What's the derivative of x squared plus 1? 2x, right? So we just have to remember to multiply in here the derivative of 2x. Same thing's going to happen here. When you take the derivative, the 1/2 will just stay because that's a constant. And then we take the derivative of natural log of 2x squared minus 1. So we have to take the reciprocal. So that's 2x squared minus 1, and then times the derivative of the 2x squared minus 1. And again, that's an easy derivative. That's just going to be 4x, right? Okay? So that I know you know. That's it. There's the derivative. Now you can simplify this a little bit, right? This is going to be 1 over x plus 2. 2 times the 2x here is 4x, right? So plus 4x over x squared plus 1, right? And then here, the 1/2 and the 4x will multiply, right, to give you what? Just 2x, correct? So you would have 2x over, and then the 2x squared minus 1. Because, 2 goes into 4x 2x times, right? So you would end up with 2x over 2x squared minus 1. Now you can leave it like this. There's no reason to try to add those fractions together, okay? That's going to be more trouble than it's worth. So you can just leave the result just like that, okay? Yeah, there it is. All right. Let's ramp it up a little bit, though. All right. All right. But it's very good now if you can get through an example like this. All right. Now, we're going to do something a little bit more exotic, though. All right. So what our text here says is we can combine differentiation of natural log, right, with implicit differentiation. Ooh, there's a term from Calculus 1, implicit differentiation, and that can sometimes, by combining those two ideas, that will give you a convenient way sometimes to differentiate complicated expressions that don't even involve natural logs, all right? So what I'm showing here is kind of a little trick that you can use to differentiate. It's really only useful with complicated expressions, even when they don't have natural log in them. So suppose that you wanted to differentiate that terrible thing, okay, x minus 2 squared over the square root of x squared plus 1. That doesn't even have natural log in it, right? Okay, so that really is a Calculus 1 problem. Doesn't even have natural log in it. But it's a really messy expression, right? And so to differentiate that, to find dy dx for this function is no piece of cake, right? What derivative rules would we have to apply here? We're not going to actually differentiate it in a straightforward way, but if we were to differentiate this in Calculus 1, you may have differentiated expressions that complicated. What differentiation rules would we have to apply? One thing I see here is, what do we have? A quotient. So when you're differentiating quotients, you have to usually use what? The quotient rule, right? Remember, there's a rule for differentiating quotients called the quotient rule. That is not an easy differentiation rule, right? Okay, that's not fun to execute. Okay, so I see the quotient rule here. I also see probably the chain rule is going to be involved in differentiating this. Okay, and I think the power rule also, because here you have a power. But the power rule for differentiation, right, means you bring down the power, right, and subtract 1. And this square root is really a 1/2 power. So I think the power rule is going to be involved in differentiating this fraction. So we could grind our way through this. It would take us a little while, but we could differentiate this just using our Calculus 1 knowledge. Okay, but now let me show you a way we can differentiate it with actually avoiding all of those ugly rules. Okay, all right, and that involves implicit differentiation and logs. Okay, so now you may have to recall what I mean by implicit differentiation. That's something that's practiced in Calculus 1. Students usually don't like it, okay, but it is a technique that's practiced in Calculus 1. And on your Calculus Review homework, right, that you're going to prepare for the first test, right, there is a problem about implicit differentiation, just to remind you a little bit of that process. But I'm going to remind you here in this problem as well, okay, of what implicit differentiation means, all right? Okay, now, here's how I'm going to do this. So I'm going to pull a little trick to start with, okay? So I'm going to take, since this is an equation, right, I'm going to start by taking the natural log of both sides, okay? So I'm going to take the natural, not differentiate both sides, I'm going to take the natural log of both sides of this equation. Since the left-hand side equals to the right-hand side, right, then the natural log of the left-hand side should also equal the natural log of the right-hand side, all right? So that's what I'm going to write down here. So I'm going to have natural log of y is equal to natural log of x minus 2 squared over square root of x squared plus 1, right? Okay? Now, you can see why I wanted to take the natural log of both sides here, right? Because now what am I immediately going to do on the right-hand side? By the way, notice I haven't done any differentiation yet, right? Okay? Remember, that was my goal, is to differentiate this, okay? But I haven't done any differentiation yet. I'm just playing around first with the equation. All right, so why did I want to take the log of both sides? Because what am I going to do on the right-hand side? I'm going to expand it, right? Yeah, see, that's the great thing about natural log properties, right? Now I can expand and break down that right-hand side, okay? And I'm going to make it look a little bit easier. So can y'all help me expand that now? So don't forget about the left-hand side is still there, right? Natural log of y is equal to, so let's see, this is going to be natural log of, what is it, x minus 2 squared minus, right? Natural log of the denominator, which is square root of x squared plus 1. And I might as well change that square root while I'm at it here. Let's change that to 1/2 power, right? Because I'm probably going to do that anyway, right? And can I break that down more? Yeah, by doing what? Yeah, bringing the powers down, right? Okay, bringing the powers down. Okay, so, well, let's do that. So I have natural log of y is equal to 2 times the natural log of x minus 2 minus 1/2 natural log of x squared plus 1. Okay, now don't get carried away. You know, these log properties are so fun, right? So don't get carried away. This is not natural log of x minus natural log of 2. All right, so you can't break that up. Okay, you can break up natural log of a fraction, and you can break up natural log of a product, but you cannot break up this natural log. So this is not natural log of x minus natural log of 2. Be nice if it were, but it's not. Okay, this is not natural log of x squared plus natural log of 1. Okay, that you cannot break up. All right, so I think that's it. We cannot break that natural log down any further. Now, I haven't done any differentiation yet, though, so I'm going to have to differentiate. So I guess now's the time, right? So here's what we'll do. We'll differentiate both sides of the equation. So I'm going to take the derivative of both sides of the equation. With respect to x, don't forget now I'm differentiating with respect to x. Remember, the original function was y equals to an expression involving x, right? So I'm differentiating with respect to x. So let's write that down. So, you know, the way you indicate that is you're going to write d over dx, right, of natural log of y, right, is equal to derivative of d over dx of, and then 2 natural log of x minus 2 minus 1/2 natural log of x squared plus 1. All right, do y'all think y'all can now do the right-hand side here? Yeah, right, because we just sort of practiced that in the previous example, right? You know how to differentiate now the right-hand side, correct? So it's going to be something like 2 times 1 over x minus 2, right? And then 1/2 times 1 over x squared plus 1, but then you have to remember to multiply in the derivative of x squared plus 1, which is what? 2x, right? Okay, so I think you can pretty easily grind through the differentiating the right-hand side there. Taylor, can you do that for me while we're talking about the left-hand side, which is harder? Oh, okay. All right. So Taylor's differentiating for us, but you know how to do it. Taylor's differentiating for us the right-hand side, and we'll ask her in a moment what she got. Okay. All right. So, but now let's look on the left-hand side, because this actually is a little bit trickier. All right. This is where you have to think carefully about the chain rule. Okay, from Calculus 1. Right, which students are always a little bit fuzzy about, but now you're going to understand it maybe better. Okay. Look, we're differentiating natural log of y, okay? But here's where you really have to watch carefully. You're differentiating with respect to what? X. But what is this variable? Y, okay? Those are different variables, all right? So that is important. If you were just differentiating natural log of x with respect to x, what would the derivative be? 1 over x, right, sure, right, okay? But you're differentiating with respect to x, not natural log of x, natural log of y. So how is that different? Okay. All right. Well, let me show you. All right. First, you still follow the same derivative rule. How do you differentiate natural log of something? Take the reciprocal, right? You take the reciprocal. So derivative of natural log of y is going to be 1 over y, okay? But now this is where the chain rule comes into play, okay? This is where the chain rule comes into play. Because y is not x. Y is a function of x. So you have to multiply in the derivative of y with respect to x. It's just like differentiating natural log of x squared plus 1. You take 1 over x squared plus 1, right? But then what do you have to multiply in? The derivative of x squared plus 1, right? Same thing here. To differentiate natural log of y, you take 1 over y, but then you have to multiply in the derivative of y. What is the derivative of y, though? That's what I was trying to find to start with. So I seem to have gone in a circle, right? Okay? Right? Okay? I'm being asked here to multiply in the derivative of y, but that was the original problem. The original problem said differentiate y, right? Okay? So I seem to have gone into, I seem to be in a loop here, right? Okay? I need to know what the derivative of y is to write this down, okay? Well, all right, look. We don't have to exactly know at this point what the derivative of y is. I'm just going to represent that symbolically. How do you write down symbolically derivative of y? Y prime, or you can write dy over dx, either one of those things, okay? Y prime is a little bit easier here, but if you want to, you can write dy over dx. So I don't have to worry about what y prime is completely. I'm just going to write down, derivative of y, that's y prime. Okay? So you have this. Is equal to, what's that equal to, Taylor? 2 over x minus 2.
And then minus
X over x squared plus 1. All right, so Taylor has very conveniently found for us there the derivative on the right-hand side. Okay? Now you're thinking, where's all this leading? We're done. Here's why, okay? What is it that we were originally looking for? We were, not y, but what? What we were trying to do there, what does it say? Yeah, so we were trying to find y prime, right? Here is y prime, okay? You can solve this equation for y prime, right? Okay, how can you solve that equation for y prime? Just multiply both sides by what? Not 0. You can't multiply both sides of an equation by 0. Okay. How do I get the y prime by itself? I have to get rid of this, right? How can you get rid of this? Multiply both sides by what? Y, right. Multiply both sides by y, correct? Okay. If you multiply this by y, the y's will cancel, and you'll just get left with y prime, right? But don't forget you have to do it on the right-hand side. So multiply both sides by y. That's what I'm going to do. So I'm going to multiply this by y, and I'm going to multiply all of this by y. So what happens on the left-hand side? Those cancel, correct, right? And what do you end up with here? Y prime. Now what's on the right-hand side? So you have 2 over x minus 2, right? Minus x over x squared plus 1. And then you have multiplied in here y, okay? Now, unfortunately, you don't want the y multiplied in there because the variable you want on the right-hand side, you only want x. You don't want y multiplied in here. But you know what y is equal to. What is y equal to? Go back to the original statement of the problem. What is y equal to? It's equal to all of this, correct? Isn't that what the problem says? Y is equal to this, right? Okay. So, in our last equation, instead of writing in the y, we can write in this, okay? And we'll be done. Let's do that. So let's write in, instead of y, let's write in that original formula for y. What was that? X minus 2 what squared? Over what? What was that over? Square root of x squared plus 1? Over square root of x squared plus 1. You're done. Okay. There is that's the derivative. Okay. Isn't that what y prime is? Derivative, right? Okay. There it is. Okay. So there's the expression for the derivative. Now you're saying, ooh, that's really big and ugly. Yeah, we knew it was going to be big and ugly to start with, right? Okay, yeah, you get a complicated expression for the derivative. We knew that was going to happen. But did we have to use the product rule here? No. Do we have to use the quotient rule? No, thank God, okay? I can't even remember the quotient rule, much less use it, right? Okay, so I didn't have to remember the quotient rule. I had to remember the chain rule a little bit, okay, but very easy, right? Okay, so that came, actually, you're thinking that took a little bit of work. No, it really didn't compared to what we were facing, okay, with just our rules from calculus. All right, so now, all right, let's review these steps, okay, because there are problems like this in the homework. This is called natural log differentiation, okay? It's a shortcut to standard differentiation. So what did we do to start with? Took the natural log of both sides, right? And then, of course, we exploited our natural log properties, right, to do what? Simplify the right-hand side, correct? Okay, then what did we do? Took the derivative, right, of both sides. But what did you get on the right-hand side? This will always happen when you're doing this natural log differentiation. What did you get on the, left-hand side? You got 1 over y times y prime, right? Okay. Now, what you get on the right-hand side depends on the expression, okay? So you get 1 over y times y prime, and then times something on the right-hand side. And then how do you solve for y prime? Just multiply both sides by what? Y. And then you have to remember, okay, what was y originally equal to in terms of x, and substitute that back in, okay? And that will be your answer, okay? All right. Let's pause for a minute now, okay? That was kind of exhausting. So I do have one more example of this, okay? But I have that in I had that in a video, but I didn't see the link to the video. I usually put those in the homework, okay? So let me see if I can find that. Let me see if I can find the link to that video for this example, which I'm not going to do in class, but I have a video of this. And let me see if I can put that in the homework. So that's another thing that I will often put at the top of homeworks are examples of videos of examples that are in the notes, but that I don't actually do in class, okay? Because we don't have time to go through the example in class, okay? So let me see if I can find that link, and I'll add it to the either the instructions or the description at the top of the homework. So this will frequently happen. We'll be going through in class examples, and I'll have an example, and I'll say, okay, I have a video of that example, and I will include the link to that video in the corresponding homework assignment, okay? All right. So let's take a break, and then we're going to go back. We have one more example from these notes, and then finally we'll be done with differentiation, and we'll move on to what was really the main thing that we were interested in with natural log, which is integration. Okay. So we'll come back at about 2:15, right? Okay, so one fast thing that I've got to mention here. Natural log functions, remember the domain starts at 0, right, for natural log functions, so you cannot take natural log of a negative value or 0. So that gets a little bit cumbersome sometimes in practice to avoid 0 or negative inputs for the natural log function. So you'll often see expressions of this form where you have natural log of an absolute value, all right? And so, except for 0, absolute value will always be positive, right? And so you'll be able to compute a natural log of an absolute value unless the u here is 0, right? Okay. So that by taking natural log of by taking the absolute value, right, of this quantity that you're trying to compute the natural log of, you expand the domain sort of the problem, right? All right, so so you'll often encounter expressions like this where you have natural log of an absolute value. But fortunately, that doesn't really alter the derivative at all, okay? So if you take the derivative of natural log of an absolute value of an expression, you get the same derivative, okay? It's going to be 1 over the expression actually without the absolute value, okay? Don't forget, though, the chain rule still applies, right? So you have to multiply in the derivative of the expression, okay? So, for instance, suppose you wanted to differentiate natural log of absolute value of cosine of x rather than cosine of x. if you just had natural log of cosine of x, see, that function is kind of problematic because remember, cosine of x, right, oscillates between -1 and +1, correct? So, so cosine is frequently negative, all right? And so if you just have natural log of cosine of x, that has a complicated domain because cosine is often negative, right? Okay, but you can simplify the domain greatly just by taking absolute value of the cosine. Okay, so that would be always positive or, but sometimes 0, because sometimes cosine is 0. Okay. All right, so let's see if we can. So natural log of absolute value of cosine of x is much easier to work with than natural log just of cosine of x. Because it has a much larger domain, but the derivative is difficult. Is easy. Okay, not difficult. Exactly the opposite. It's not difficult. It's easy. So let's see if we can. Let's see if we can differentiate that. So again, the way to express that, right, is just write a d over dx, right, of a natural log of absolute value of cosine of x, and as I just said there, right, that derivative is just the same as derivative of a natural log of cosine of x without the absolute value bars, okay? So you're going to take the reciprocal of cosine of x, so you have 1 over cosine of x, okay? But don't forget the chain rule, right? You must multiply in the derivative of cosine of x. What's the derivative of cosine of x? What now? Negative sine of x, right? So one thing that we're going to have to remember, right, is our derivatives of the trigonometric functions. Okay, some of them you'll remember easily, right? Okay, others are a little bit less easy to recall. We're going to review those a little bit in the next notes, all right? But the derivative of cosine of x is minus the sine of x, so that one's usually one that you remember. So you have minus sine of x over cosine of x, and what's sine of x over cosine of x? That's better known as tangent x. So this is minus tangent of x, right? Just that easy. So taking derivative of natural log of an absolute value is really no different than taking a derivative of natural log without the absolute value. That's one of the convenient things, another nice convenient things about natural logs. Okay. All right. Here's our last example then from these notes. Okay. There's actually 2 parts of this, but we're only going to try to get through one part, and then we'll come back and do the next part next time. Okay. So here's what you're asked for. This is another familiar problem from Calculus 1. So this is a problem that you solve frequently in Calculus 1. So we'll have to remind ourselves of how to do this problem. It does require some steps. It's not one of the easiest problems from Calculus 1. Okay. And so we'll review here a little bit. It says locate the relative extrema of this function. So natural log of x squared plus 2x plus 3. So remember, relative extrema, there's 2 types of extrema. There's a relative maximum and a relative minimum. Okay, and remember, relative maximum, that corresponds to the peak points on the graph. So when you're thinking of a relative maximum, that just means where are the hilltop points on the graph of the function, and relative minimum is the valley points on the graph of the function. Actually, we're not using that terminology quite correctly, okay, as I'll explain here, but this is the way it's always used. All right, so what we're looking for here are the peak points, right, or the valley points on the graph of this function, natural log of x squared plus 2x plus 3. Now, this may be a kind of an invalid question because, graphs are not required to have peak points or valley points, right? Graphs are not required to have a relative maximum or a relative minimum. Together, we call those the relative extrema if you combine those 2 ideas. Okay, so the answer to this question may be none. All right, but let's take a look at the graph of natural log of x squared plus 2x plus 3 before we start trying to answer this question, just to convince ourselves that the answer to this is not none. All right, okay, because that wouldn't be a very fun question. if the answer is none. So as usual, right? As I'm usually going to do in this class, I'm going to make a graph here using Desmos. Okay. So here is the graph of natural log of x squared plus 2x plus 3. There it is. Okay. So you get this nice curve, right? Kind of wishbone-shaped curve here, and indeed it has a, you notice it has a valley point on it. So this is a relative minimum, okay? It actually is a minimum because there are no points below this one at all, okay? But in particular, it's a relative minimum, all right? Actually now, I said that terminology is not correct. Actually, the relative minimum is the y-coordinate of this point, okay? That is actually the relative minimum, is the y value for that point. But we usually just say the point is the relative minimum, okay? So we usually give the answer as coordinates, all right, rather than just the y-coordinate of this point. So what does it look like? The relative minimum is there. It looks like it occurs at x equal minus 1, right? I'm thinking that's going to be my answer here, or at least the first coordinate of my answer. And it looks like the y value is something like, what is that? Yeah, that's harder to see, right? Okay, something like 0.75. And see, this is 1/2, and this is 1. So, yeah, but so we could estimate it as about 0.75. But I wonder how close that estimate is to being correct. So, of course, we want to give the exact answer, right? So, of course, we want to use calculus to give an exact answer. Correct. Actually, let's point at it with Desmos here and see what Desmos tells us. So it says, am I pointing at that point? Yeah, I think so. So Desmos says that's minus 1 and 0.693. Okay, not 0.75. Okay, all right. So now I wonder where Desmos got the 0.693. So let's see if we can confirm that. Okay. So, but it certainly looks like we have a relative minimum, and at approximately those coordinates, right? Minus 1 and 0.693. Now, we have to remind ourselves, though, how do we actually find extrema, right, with calculus? So how do we locate where those extrema might possibly be? And then how do we verify that our possible points really are extrema, okay? So you recall it's kind of a two-step process. First, you have to figure out where the extrema might be, and then you have to actually verify that your possible extrema really are extrema. Because what will happen sometimes is, in calculus, you will locate points that may be a relative maximum or may be a relative minimum, but they turn out, when you look at the graph, they're not actually a relative maxima or minima, okay? You sometimes get these kind of false alarms, all right? So so we have to first figure out where they might be, and then we have to really check to see if they really are maxima or minima, okay? All right, so how do we, if we look at that graph again, how do we figure out where that point right there might be? What's happening at that point that's kind of special? That kind of gives us a clue to where to hunt for it. There's a turning point there, right? Okay. There's a turning point there, okay? So actually that language is quite nice. There's a turning point. Turning point means the graph is switching from what? From going down, right? That's called what? Decreasing, yeah, to, in this case, going up. That's increasing, right? Okay, so a turning point is where the graph is switching from decreasing to increasing, okay, or vice versa, all right, from increasing to decreasing. Here it's switching, obviously, from decreasing to increasing, okay, but it could be switching the other way, okay, at a turning point, okay. All right, so turning point where the graph is switching from decreasing to increasing or vice versa. So if you have a point where the switch occurs, what's happening right at that point? Is it increasing or decreasing at that point? Yeah, let me repeat the question, okay? So a turning point, right? That's where one of these relative extrema is going to be, okay, where the graph is switching from increasing to decreasing or vice versa. So at the point itself, is the curve increasing or is it decreasing? At a turning point, is it increasing or is it decreasing? It's what? Neither, right, okay, right? Because that's where the switch occurs, right, okay? So at a turning point, a possible, a relative maximum or possibly a relative minimum, right, okay? It's neither increasing nor decreasing, okay, right? Neither increasing nor decreasing. Now, how do you tell from calculus, what determines if a curve is increasing? What has to happen for the curve to be increasing? How do you check that in calculus if a curve is increasing? What happens where a curve is increasing? What? Yeah. What are you checking? Someone said it. What? You check the slope, right? Okay. By slope we mean slope of the tangent line, right? Okay. Slope of the tangent line. How do you determine slope of a tangent line? Derivative, right, okay, yeah. Derivatives give you slopes of tangent lines, correct, okay? Derivatives gives you slope of tangent line. So where a curve is increasing, you're looking for the derivative to be what? Positive, right. I see a lot of phones, okay? So that's got to stop. So those phones, no, you don't just slide that somewhere. You put that phone completely away for me, right? Then zip your bag for me. Yeah, okay, right. Same thing over here, right, if I see phones, right? I want phones. Don't want to see phones, okay? All right. All right, so where the curve is increasing, right, okay, that means the derivative is positive. What about decreasing? Derivative is negative, right? Well, we said at a turning point, okay, the curve is neither increasing nor decreasing, so what's the derivative going to be? Zero, right, okay? There, the derivative is going to be zero. That's the clue, right? Okay, that's the key, right? Remember this from calculus? You look for turning points. That's either a local maximum or a local minimum, right? You look where the derivative is what? Equal to zero, right, okay? You look where the derivative is equal to zero. Now, there actually is one other strange case. You also have to look where the derivative is undefined. There's also that possible case. But typically, it's where the derivative is zero, okay? An x value where the derivative is zero or undefined, that's called the critical value, okay? Remember the terminology critical value, all right? So you're looking for the critical values. That's where you can find the relative maxima or the relative minima, okay? Or local maxima, local minima is the same terminology, all right? You're looking for critical values where the derivative is zero or where the derivative is undefined. So, how do we find where the derivative is zero? That's right. You take the derivative and you set it equal to zero. Very common thing in calculus, right? Very common task in calculus. Take the derivative, set it equal to zero. Do that all the time in calculus, right? The reason you're doing that is you're looking for critical values, right? Okay. All right. So, well, here we go, all right? So we're going to try to find the critical values. That's the x values where the local maxima or the local minima or relative maxima can occur. We're going to find those by setting the derivative and set it equal to zero. All right, so can we find the derivative of natural log of x squared plus 2x plus 3? Ooh, I hope so. All right, so how do we find that derivative? All right, so what is that derivative, folks? So this one's an easy one. How do we find the derivative of a natural log? What now? Cannot expand that, okay? If that were natural log of x squared times 2x times 3, then I could expand it, okay? But you cannot expand this, all right? But you don't really need to expand it. It's pretty easy to differentiate just as it is. Again, what's the basic rule for finding derivative of a natural log? What do you do? Yeah, 1 over the expression, what's that called? Begins with an R. Reciprocal, right? Take the reciprocal, right? Okay, you take the reciprocal. Try to memorize that simple phrase, right? Derivative natural log is the reciprocal, okay? That will really help you on test. So let's see, this derivative is going to be 1 over x squared plus 2x plus 3, but the chain rule comes into play, right? So what do I have to multiply in here? The derivative, which is what? 2x plus 2, right, okay? And now what am I going to do with all of this? I wasn't just finding the derivative for fun, right? What am I going to do with all of that? Set it to 0, because what am I looking for? Critical values, right, okay? I'm looking for the critical values. All right, so we set this to 0, and that gives us this nice equation, 2x plus 2 over x squared plus 2x plus 3 is equal to 0. Now we have to solve this equation, or don't forget the other possibility. It usually is not relevant, but sometimes it is. The other possibility is where the derivative is not defined. Okay, so you have to be careful about that. All right. Well, let's not worry about where it's undefined here. Okay, let's just worry about where it's equal to 0. So we have this equation equals 0. So we have to solve that equation. Any suggestions on how I can go about solving that equation? Multiply both sides by the bottom part, because I really don't want to see the fraction there, right? That's really, fractions and equations are kind of messy, right? So I can get rid of the fraction by multiplying both sides by the denominator, the bottom part, x squared plus 2x plus 3. Don't forget to multiply both sides, though. But, of course, in this equation, the right-hand side doesn't make much difference, because when you multiply this by 0, what do you get? 0. So you just get 2x plus 2 equals 0. What a nice equation to solve, right? I think that just says what? X equals minus 1. That is our only, so far, critical value. Is that what we saw in the graph? Yeah, right. That's where the turning point was, right? At x equals minus 1. So that, on paper, that we've sort of confirmed there what we see on the graph, or the graph sort of confirms what we found here on paper. Now, remember, there can be another critical value where the derivative is undefined. Is it possible? Here's the derivative, right? 2x plus 2 over x squared plus 2x plus 3. Is it possible for that to be undefined? It is, maybe, okay? Because that's a fraction, and when are fractions going to be undefined? When the denominator is 0. So you have to be careful about trying to figure out, is there an x value that will make the denominator 0, okay? So that means you also have to think about this equation, x squared plus 2x plus 3 equal 0, all right? That's a quadratic equation. How do you solve quadratic equations? It's quadratic because the x is squared. How do you solve quadratic equations? You might factor, okay? Factoring is a good method. Or if factoring doesn't work, what's your other option here? Quadratic formula, right, okay? These are all things you're going to have to use at various times in the course. Well, this x squared plus 2x plus 3 does not factor, okay? But, so if you try using the quadratic formula, I invite you to use the quadratic formula to try to solve this, and you'll see this equation has no solutions, okay? If you try using the quadratic formula, you'll see that the equation has no solutions. So that's great. We don't have to worry about where so I'm not going to go through that. You can try the quadratic formula yourself, and you'll see that this equation has no solutions. So that means we only have one critical value. This is it, okay? So that is the location of our possible turning point. Now, we've already seen on the graph that that really is a turning point, right? So we already are pretty convinced, right, that we're going to, in fact, have a local minimum, right, because that was a valley turning point. We're going to have a local minimum at x equals minus 1. What's the y coordinate then? So what's the matching y value here? Well, take that and plug it back into the original function, right? In other words, compute f of minus 1. So that would be the natural log of minus 1 squared plus 2 times minus 1 plus 3. What does that add up to? Is that natural log of 2? Is that right? Because this is going to be 1, right? This is 3, so that's 4, but you're subtracting 2, correct? So you get 4 minus 2, which is 2. So there is your y-coordinate natural log of 2. So that is our possible turning point, okay? Now, again, since we already made the graph, we already know that that really is a turning point, right? But if we play dumb here, if we weren't looking at the graph, okay, then all we would know at this point is we have a possible turning point at minus 1 and natural log of 2. By the way, how much is natural log of 2? You'll need a calculator for that, okay? What is the natural log of 2? What? Is it 0.693? Oh, all right. So, so Desmos knew that really well, right? Okay, because that's what Desmos said also. Okay, that y-coordinate of that turning point is 0.693. Okay, so that's our possible turning point at this point. Okay, now, we have just enough time to remind ourselves. How do we verify now that that really is, if we didn't have the graph, so if we were just flying blind here and we couldn't see the graph, how could we verify that that possible turning point really is a turning point, okay? On pencil and paper, analytically, how could we check that, okay? So how do we check that there really is a turning point at minus 1 and natural log of 2, okay? All right, so that is how we, that's the last step here. All right. Okay. What we're going to do here is we really cannot work without the graph, okay? But I'm just going to work, so I'm going to actually kind of draw a graph here, but it's really going to be an ugly, messy, simple graph, all right? It's going to be very rough, all right? So let's see. There's our critical value, right? That's minus 1, right? On the x-axis, right? Okay. So that's a minus 1 there, all right? All right, so here's what we're going to do. Again, what happens at a turning point? What happens to the graph at a turning point? What happens to the direction of the graph at the turning point? It changes from what? Increasing to decreasing, or possibly what? Decreasing to increasing, right? In other words, it changes direction, okay? At a turning point, the graph changes direction. It's either it goes up and then goes down, or it's going down and it changes to going up, right? Okay? All right, so what we'll do is, let's see what the direction is over here on the left of minus 1, and let's see what the direction here over is on the right of minus 1, okay? If that direction changes, then we'll know, oh, yeah, there really was a turning point there at minus 1. All right, so let's pick a number there a little bit to the left of minus 1. Y'all can pick any number you want. So what number do y'all want to choose there? Negative 2. That's kind of easy, right? Okay. And then let's pick a number a little bit to the right of minus 1. It can really be any number you want, but what's a convenient one? Yeah, I like 0, right, because it's usually easy to do arithmetic with 0. How do you check the direction of the function at these numbers? Plug it into what? Not the original function. The derivative. It's derivative that gives you direction, right? Okay. The original function just gives you the output, right? Okay. It's the derivative that gives you the direction of the function. Okay. All right. So plug those numbers into the derivative. Do we know what the derivative is? Where's the derivative? Not sure I ever wrote it down, but that's it, right? There is the derivative. Okay. All right, let's start plugging 0 in because that's easy. So in other words, I'm going to calculate f prime, that's the derivative, right, of 0. Here's the formula for the derivative, okay? There's the formula for the derivative. So when you plug 0 in there, you get what? 2 times 0 plus 2 over what? 0 squared plus 2 times 0 plus 3. What is that? Is that 2/3? Right? okay, which is greater than 0. So what does that tell me about the direction at 0? It's increasing, right, okay? So I know the curve is going up. I have no idea what the curve looks like, right? If I haven't made a graph, I have no idea what the curve looks like. But I know it's going up. Now let's try it at -2, okay? So plug -2. Be sure you plug it into the derivative. So we're going to calculate f prime of -2. Can someone do that for me? F prime of -2. Someone calculate that. But I'm going to tell you that when the person tells us what that is, that's going to be negative. Does it come out -2/3? Is that what it is? So it's symmetric there. So it comes out as -2/3. So that means over here at -2, the curve is falling. So to connect that decreasing and increasing part, what had to happen at -1? What did you have to get? A 0 what, though? No, the curve doesn't go down to 0, but what does go down to 0 at -1? The derivative, okay? So what kind of point do you get here at -1? How do you connect a decreasing piece to an increasing piece? What do you have to have there? You have to have a turning point, right? Okay, yeah. The only way to connect the decreasing piece to the increasing piece, right, is to have a turning point right there at -1, okay? So we do have a turning point at -1. We've confirmed that. Of course, we already knew that secretly from the graph. What type of turning point is it? Where you reach a valley like this, what's that called? No, there's no such thing as a positive turning point, okay? That's a local what? Minimum. This is a local minimum, or you also sometimes say relative minimum. That's a local minimum, okay? So when it switches from falling to rising, you get a local minimum. If it switched from increasing to decreasing, you would have a local maximum. So we're done. There it is, okay? We've confirmed. Because the derivative changes sign from negative to positive, that means not only do we have a possible turning point, but we have a legitimate turning point, and it's a local minimum. So we have a local minimum at -1 and natural log of 2, which is about 0.693, okay? All right, so do y'all remember this process, sort of? Yeah, okay, we're going to have to practice it in the homework. Now, I cut off half of the problem, which we're going to come back to, because remember, we're not always just interested in turning points. What other type of point on the graph is interest to us? Do you remember? Inflection points, right, okay? Ooh, inflection points. What were inflection points, okay? What happened at inflection points? We're also interested, by the way, in x and y intercepts. I should point that out. This does not have any x-intercepts, though, okay? But it does have some inflection points, okay? So we also want to be able to remind ourselves, how do we find what are inflection points to start with, and how do we find them, okay? All right. So I'll see y'all on Monday, right? So I think you can make a pretty good stab at finishing your homework, all right, that first homework assignment.